We're going to take a look at perpendicular and angle bisectors and how we can use those to find various parts of missing parts of figures. So we're going to start by just defining these terms real quick. So this definition will be that a segment, line, or ray, so a perpendicular bisector is a segment, line, or ray that is perpendicular to and bisects another segment. So having a perpendicular bisector allows us to know a few things about a figure. So we're going to go through what's called the perpendicular bisector theorem. So this simply states that any point on the perpendicular bisector of a segment, so like point D in the figure, is equidistant. So the same distance from the endpoints of the segment. Okay, so our point on the perpendicular bisector is D. The endpoints of the segments are A and B. So what we're saying is that the distance from A to D and the distance from B to D are the same. Or if we make this little triangle, these segments are congruent. So we would say AD, that distance, is equal to BD. Okay, so we're talking about distances. Okay. So the converse of the perpendicular bisector theorem is also true. So if we know that a point is equidistant from the two endpoints of a segment, then it must be on the perpendicular bisector of that segment. Okay. So in other words, if we had this scenario, right? So if we knew that these two were congruent, then we know, so if we had this here kind of, if we knew that those two segments were congruent, then we knew that this would be a perpendicular bisector of that edge down at the bottom. So it's just sort of reverse order of knowledge from what we previously did. So this next definition should be familiar to us. It's an angle bisector. Angle bisector is simply a line or ray that splits an angle into two congruent angles. So what we're going to add to that is this new portion, which is our angle bisector theorem. So our angle bisector theorem states that any point on an angle bisector is equidistant from the sides of the angle. So here, BX is our angle bisector. And we're saying if we take that point X, it is equidistant from the sides of the angle. So what that means is when we draw the shortest distance from that point out to the angles, and the shortest distance is going to be at a right angle, we know that these are congruent here. Okay, we know that those are congruent. So our conclusion here would be that AX, the measurement of AX, is equal to the measurement of CX, or those two figures are congruent. So let's take a look at applying some of these ideas. So if we take a look at this figure, we want to go ahead and fill in some information about the missing pieces. So the first thing that I'm going to notice is that I do have a segment that is being bisected. So segment BD is being bisected by segment AC, and it's being bisected at a right angle. So that tells me that AC, hold on, let me get a reasonable pen size here. So we know that AC is a perpendicular bisector of BD, right? So AC is a perpendicular bisector of BD. So because of that, we know some things about the perpendicular bisector. So namely, what we know is that a point on the perpendicular bisector is going to be equidistant from the endpoints of the segment being bisected. So here, A is a point on the perpendicular bisector, and because AC is a perpendicular bisector, we know A is going to be equidistant from the endpoints of that bisected segment. And we kind of know the other thing on the other side. So C is also a point on the perpendicular bisector. So it is also going to be equidistant from the endpoints of our segment. So that means BC and DC are going to be congruent. So now that we've marked these congruencies, we can go ahead and fill in some missing pieces. So if AB is 5, then we know that so would AD be. Oops, actually, I should change these tick marks. That should be 2 and then 3 because we already had a single tick mark congruency marked on there. Okay, so then if DC is 20, then BC also has to be 20. So let's go ahead and fill those in where we needed to down here, and then we're also going to add in that ED should be 4. So we know ED should be 4, AD is 5, BC is 20, and we need to find these other 3 side lengths. But the nice thing is that we're in a right triangle. So we can just use Pythagorean theorem to go ahead and find those side measurements. Okay, so side AE is we're going to solve the A squared plus 4 squared is equal to 5 squared. So you're going to use that setup of the Pythagorean theorem here. So we would get that A squared is equal to 9, not 9 squared, just 9, which means A is equal to 3, or AE is equal to 3. And then, so we can go ahead, put that on there. And then we want to find EC. So we know that we can solve the Pythagorean theorem. We can set up that 20 squared equals 4 squared plus, we're just going to call it A squared for now. And we're going to go ahead and solve that. So we're going to take 20 squared minus 4 squared. This is where a calculator comes in handy. We get 384 equals A squared. Take the square root, and we just want to always leave our answer as the most simplified radical form. So we're going to get 8 root 6 equals A, or the length of EC. So this was 8 root 6. Well, now it asks us to find the length of EC. Well, EC is just AE plus EC. So we're just going to simply write that as AE 3 plus EC 8 root 6. We can't necessarily simplify that any further. We're just going to leave it like that because we do want the most exact value for our answer here. So even if you just type that in your calculator, if you're working with a scientific calculator, it should just leave it in that form. So that's working with a perpendicular bisector. So let's take a look at what we can do with an angle bisector here. So looking at this figure, we can tell that AC is the angle bisector of BAD, right? So we're bisecting this angle right up here. So what do we know about that then? Well, because we have an angle bisector, we know that any point on the angle bisector is equidistant from the sides of the angle. So we can say that BC, length of BC is going to be equal to the length of DC. So we're going to use that to solve for x here. So that tells us that 10x plus 6 needs to equal 14x minus 10. So we can go ahead and do a little bit of work here. So we'd get 16 equals 4x, or 4 equals x. And then we can use that to substitute back in. So up here we would have 10 times 4 plus 6, and that will give us 46. And because these are congruent, we should have that this is 46 down here as well. So now we have found these 2 lengths, DC and BC. Okay, but it's asking us to also find some angle measurements. So the first thing we can see is that in the sort of upper triangle, we can apply our triangle angle sum theorem. And we know that this angle right here, angle BAC, is going to be 180 degrees minus the two existing angles that we know. So minus 90, minus 57. So we know that that would be a 33-degree angle. And then we also know that angle DAC, that would also be 33 because those two are congruent. So we have a couple of things that we can fill in here. So we can fill in that angle DAC is 33 degrees, and then the other one we said was also 33 degrees. So we just need to find this missing angle down here, angle ACD, and we can do the same thing, triangle angle sum theorem. It's going to be 57 degrees, so it's actually congruent to that other angle as well. Okay, so last thing we want to find out is the measurement of AB. So because these triangles have so many congruent pieces, we are able to say that these triangles are actually congruent. So there's quite a few of our triangle congruencies we can use. So we have side, angle, side going on here, as well as angle, side, angle. So those are all triangle congruencies. So if we're looking at this and we're trying to find the length of AB, well, we are able to say that AB is going to be congruent to AD, so it is going to be 15 for its length.